Okay, 11 o'clock, the first Sunday of the month, which means it's time for Chai and Why at Prithvi Theatre. So welcome everyone, our in-person audience here, those who are watching online. And it's always a pleasure to come back every month here to bring you something from the world of mathematics and science and everything else that happens at TIFR. For those of you who've either come to the Homi Bhabha Center or to TIFR in the last 2 days when we celebrated National Science Day, you've got a glimpse of it. But otherwise, sorry, my voice is gone after being on the ground all of yesterday and day before. But it's a pleasure to introduce Professor Anand Sawant. But before I come to that, in case somebody is here for the first time or is watching for the first time, Chai and Why is an outreach offering of TIFR in Mumbai. It happens on the first of the month, first Sunday, 11 o'clock at Prithvi Theatre here. Third Sunday, typically Ruparel College. We'll let you know if that changes. And if a month has a fifth Sunday, we are online from a lab in TIFR. So on that note, let me tell you a little bit about Anand. So Anand actually was a PhD student at TIFR many, many years ago. And I think he had even done a Chai and Why in 2013 as a PhD student, which tells me that Chai and Why is going on for a while now.
Yeah, that's great to know.
After graduating from TIFR in 2014, he went to the LMU, the university in Munich, and was a postdoc there. And he joined TIFR again in 2018 as a faculty member. And he works in the area of algebraic geometry and topology, etc. But today he's chosen a topic which is, I have no idea what the connection between college admissions, train reservations, and stability of relationships is. But Anand is known for making maths understandable. So on that note, I'm going to leave it to him. A request to the online audience, please ensure your phones are on silent. Sorry, to the in-person audience. The online audience, of course, your phones can ring. It's perfectly fine. You will not get chai, but you can, of course, put in your questions. Now, the only way we can get your questions is if you put it on the chat in YouTube. So please do that if you have a question. I will try and enter into a stable relationship with my phone and a network and see if I can join the YouTube chat. And if there are questions, I will let you know. Okay.
Great.
If you have questions, of course, raise your hand and ask them anytime. If there's a in-person question while we are online, just repeat the question so that the
online
audience knows.
Yes.
After the chai break, of course, we will have a very closed discussion here. That's not going to be online. So you get an extra something for coming here. Okay. So thank you very much for coming, and over to you, Anand.
Thank you very much, Arnab and Ullas, for the invitation to speak at Chai and Why. As Arnab mentioned, I spoke here in 2013, which was a long, long while ago. And it's great to come here again and see all of you, people. Now it's new people, but it's great because it's great. It tells me that Chai and Why has been running successfully for a long, long time. And the tradition should continue and continues. Okay. So now I think, sure, I need to share my slides. Yes, so I share my screen first. Okay, so is my screen visible?
Yes.
Okay.
One second, let me just check on YouTube that it's visible.
Yeah. Okay. We are good to go, right?
Yeah, I think there's a small delay, but yes, we are good to go. You're on YouTube. Yes.
Okay. Yeah. Okay, great. So before we begin, I want to ask everybody. Yeah, so first of all, thank you for coming here on a Sunday morning. Do you prefer English, Hindi, or Marathi? Mix. Whatever. Okay. So please feel free to stop me anytime and ask for explanations, or if you want me to explain it in a different language, please feel free. Okay. All this activity, the main aim is to informally understand something, as we all try to do. Our job as scientists, mathematicians, is to understand the phenomena that occur in the world. And this is an attempt to take it to public. Okay. So yes, I'm going to talk about this title, which may or may not sound a little bit catchy: college admissions, train reservations. So, okay, so these processes, we see in our day-to-day lives, right? So all of us, when we finish our school, this is the first time it comes when we are seriously applying to college. Okay. Now we have a certain list of colleges in mind. We have our own preferences. We want to go to a college that is good, that's reputed, that gives us better opportunities after going ahead, after going through that college. And also we have some constraints. We don't want it too far from our home. Okay, or maybe we want the life in the college to be nice. Okay, so on and so forth. Everybody has different personality. They have different constraints. And so ultimately we come up with a list of preferences. Okay, but then the other problem comes. Okay, we want a certain college, but a certain college may not want us. Okay, so this is what happens to all of us. Has happened to me, I'm sure has happened to you too. Okay, so then what do we do? So there is a process, that for this, you apply to a college, then a college brings out what is called a waiting list. Okay, then you wait, then you see it has already made offers to some people. Then those people accept those offers. Some of them don't accept those offers for whatever reasons. And then the college will have certain seats still empty, and then it will put out a second list. Okay, then we see if we are on the waiting list or not. Or we either get our name in the list or not, and then this process continues. Okay, this process has to stop at some point, because at every point there are only some certain number of seats available, and they go on running out, or sometimes they remain vacant. Okay, now if you see train reservations, okay, it's a similar system, right? So I just put on this IRCTC portal where you usually, this is what you usually do, and then it shows, certain trains, certain train is departed, there is a wait list, or tickets are available, so on and so forth. It's basically the same principle, right? You apply, you want a seat there, you may not get it, but you're on the waiting list, and then whenever it becomes available, then it's your chance. Okay, that's how this goes. But then the question that I want to ask is, who do these processes actually benefit? Are these good processes? Okay, are these fair? How many of you think that these processes are fair? How many of you think that these processes are unfair?
What do you mean by fair?
That's again, it's a personal perspective. This is, by fair, unfair, I don't mean any scientific thing. I just mean a personal perspective. You like the process, you don't like the process. It's the same thing, it will come to you. We just apply. We apply, then the college thinks about our application and then puts out a waiting list. Okay, puts out a selection list and a waiting list. Okay, if we get selected, then we have a choice whether to join or not. Otherwise, we wait, and we wait until our number comes up. Okay, and this continues. Okay, this is the process. Okay, so the idea is to give some sort of an answer to this question. Okay, you can hold out your, I'm pretty sure you all have an opinion. You may not have spoken it out loud, but you have an opinion if this process is good or not. Just, keep it with you, and let's just see what falls out of this. Okay, but I'm a pure mathematician, and what we do in pure mathematics, well, uh, many people think that pure mathematics is, it's pure, it's not applied, so it's not applicable at all, so it's useless, which it is. But I mean, if you think about it, but the intellectual exercise is still very good. I'll tell you why. Well, by the way, I don't want to classify pure mathematicians into pure and applied, because I think all mathematics is applied mathematics, because pure mathematics is application to aesthetics. Okay, so but we are not doing this just because it is beautiful. Okay, what mathematicians do is that they try to find the crux of the problem. They want to abstractify it. It is well and good if you can feed that abstract data into a computer who would do some processes and spit out an answer which you can use. Okay. Now, where do mathematicians come into picture? To theoretically make sure, or not make sure that the process gives you a desired outcome. Okay? So what I mean, I'll explain to you by the end of the talk. So as you might know, mathematicians like to talk about puzzles. So let's talk about a puzzle. Okay? So let's talk about a card game. So suppose that we have a deck of cards, 52 cards, right? 13 of each type. And suppose that I shuffle them up and I make 13 piles of 4 cards each randomly. Okay? And now I ask the following question. Is it possible to select exactly one card from each pile of 4 so that the 13 selected cards, so it will be one each of ace, 2, 3, up to jack, queen, and king. They may not be of the same color, but can you get this? That means something like this is allowed. Okay? So you have a spade, ace of spades, 2 of hearts, and so on. They're different, but you get all 1, 2, 3, up to 10, and jack, queen, and king. Can you do this? Okay? So do you get the question? Okay? Please do ask me if, yeah, please.
Is it possible means, are you asking what is the chance that I will select such a?
So for example, I have shuffled my cards. I have kept 13 piles of 4 each randomly. I'm just asking you, is it possible? Is there one choice where I can choose one from each and can make a full set from 1 to 13? This is the question.
Possible, but it may not be a very common thing that will happen if you do it.
Yeah. Possible, but not probable. Yeah. So can you say for sure that it is possible? Can you prove that it is possible? And may I know how?
Because you can arrange the cards in a particular way. So there will be so many permutations.
No, this is the thing that you cannot, you have not arranged them in a particular way. It's random.
The entire space is going to be a certain set of permutations and combinations.
Yes.
So there is one set of, in the large set, there could be one where I pick up the one card from each of them because of that. And
But how do you know for sure that you can pick up one?
It's again a probability of that. But then again, it comes out to probabilities of choosing 1 in 4.
So I'll tell you the total number of choices in making these piles, right? So you have, so how many? You choose 4, right? You know that it's a huge number of possibilities, right? So I mean, can you, if you actually, so it's a nice exercise to calculate in how many ways you can do this and see if a computer can do this, okay? But if you calculate the total number, it will be such a huge number that it's pretty much impossible to make, to examine, we don't have enough time to examine all those possibilities and pick one, okay? So what I mean to say is that yes, it looks fine, but it is difficult to be sure that I will be able to do this. Okay? In mathematics, so what is the difference between mathematics and sciences? What sciences do is that they observe what is happening in reality and they try to explain it. What do mathematicians do? Mathematicians do things, mathematicians prove things. Mathematics is about logical deductions. Okay, so you start with certain assumptions, you want to reach certain conclusion, and you are allowed to go from hypothesis or whatever your assumptions to conclusion in only logical arguments. Okay, so what we feel, what may be true, what may not be true, doesn't qualify as mathematics because mathematics wants to be exact. Okay, you need an answer for sure or not. Okay, mathematics is about taking every statement and saying whether it is true or false. Okay, there's nothing in between, may be true, may not be true, so on and so forth. But anyway, it's a question. Okay, this is a question. And so let's leave this question. Let's come back to this question at the end. Okay, let's go to another question. So all of you know what this is, right? Sudoku. You see these in newspapers. Okay, so you usually have a grid of 9 by 9. Certain numbers are filled. And then the puzzle is to fill numbers in these empty spots such that every row and every column contains all 1 to 9, but appearing exactly once. Okay? And all of us, some of us like to solve these things. We solve it, and usually a solved Sudoku looks like this. Okay? Now let me ask you a following question. Suppose that I have a solved Sudoku. So of course, how do people who set up Sudokus, how do they work, right? They take a solved Sudoku and then they remove certain numbers, okay? And then they give the rest as a puzzle. Okay? That's how they do. Now let's assume that I am somebody who is the Sudoku setter. And I have this solved Sudoku with me. Okay? So I have it on a piece of my paper. These days, of course, we have mobile phones and so on and so forth. But let's say that I am a dinosaur. I have it on a piece of paper. And suppose that by some mistake, some few rows are torn off. Okay? What do I do? Now I want to get to a full Sudoku again. Can we reconstruct a Sudoku starting with this? The question makes sense? Okay, so this bottom part is torn off. I have lost it. Okay, now I want to set the Sudoku again. So I want to get to a solved Sudoku again. Is it possible? Can we reconstruct? Okay, proof. I'm a mathematician. I'm going to ask for proofs. And if it's not a proof, I'm not going to accept it.
There are multiple solved Sudokus in this case.
Yes, how many? I'm just joking, don't worry. Yes, so the thing is that we'll see. And then there's also another question. Is there one way or are there multiple? It's a valid question. That's all I'm saying. Okay, we have to ask questions. Is there a way or are there multiple? If there is one, then are there multiple? Okay, it's a question. Now I'm going to ask you this question. What's common to all these 4 questions? We have seen 4 things, right? College admissions, train reservations, card game, and reconstructing Sudokus. Do these have anything in common? Okay.
Choice of number you put there.
Yes, we make a choice. Yes. Yes, yes, yes. So our aim is by the end of the talk to understand if these have something in common. Okay. And in fact, it turns out that there is a common mathematical principle at the base of all these 4 things. Okay. And to explain that, I am going to talk about a 5th thing that I have not come to, and that was in the title. Okay. Stability of relationships. Okay. So let's take a toy example and go ahead. Okay. You can do these things with more. So of course, relationships means people, right? So we're going to talk about people. We are going to see some experiments. Okay. So let's look at the so-called relationship problem. There are 3 boys. Let's call them Adam, Bill, and Chris. And suppose that we have 3 girls, Alice, Betty, and Cindy. Okay, suppose that our community is really small, consists of only these 6 people. And suppose that there is a matchmaker. Okay. And suppose that they have all confided in just the matchmaker, who is a he or a she, we don't know. And they have told the matchmaker their preferences. Okay, and it's the matchmaker's job to make pairs. Okay, this is the baby example that we are going to consider. Okay, so now what should the matchmaker take into consideration? Preferences of both of them. Okay, so they have all confided in the matchmaker and they have told the matchmaker their preferences. Okay, so of course, yeah, I have to look at each of their preferences. There are 6 of them. Okay, suppose that the boys have given the following preferences. Okay, so that means Adam prefers Alice the most, then Betty, then Cindy, and so on. Okay? And suppose that the girls have also given their preferences. Okay? So they go like this. Okay? And now the question is for the matchmaker to make pairs. Okay? So let me keep the tables so that for your reference. And suppose that the matchmaker just doesn't think much and makes the following pairs. Okay? Let's combine those whose names start with the same letter. Okay? So he or she pairs Adam and Alice, Bill and Betty, and Chris and Cindy. Okay? Now the question is this a good arrangement? Why? Yes, but now it's least preferred. Yes, that's correct. Absolutely correct.
Chris and Cindy are indicated they prefer each other the least.
No, Chris actually, so Cindy is in the middle, number 2. Yeah. So, okay, let's see. So you are all right, but I want to actually point out a more serious problem. Okay. So yeah, the matchmaker is going to lose the reputation because they have not paired people optimally. Because in this particular circumstance, the biggest problem that's there, it's not about whether somebody gets their top preference or the least preference or something like that. Here, the danger in this small community of 6 people is that Bill and Alice can elope. Right? Why? Alice is paired with Adam. Yeah? Alice likes Bill the most. Okay? But it takes 2 to tango. Only if Bill prefers Alice, then there's a problem, right? If Bill doesn't prefer Alice, there's no problem. But look at Bill. Bill is paired with Betty, but he prefers Alice. Right? This is the problem. Okay? It can happen that somebody is someone's least preference or most preference and so on. But if they're not preferred by other people also, then they're not going to be any other takers. Okay? Here, the problem is that this is the problem. Bill and Alice are not paired optimally. They both like someone else. I mean, they're both paired with someone compared to whom they prefer Bill prefers Alice to his partner and Alice prefers Bill to her partner. Okay, so this is the problem. So now the question is of a more complex nature. Is it possible for us to make the match, to help the matchmaker? Is it always possible to make matches which will be stable? That's where the title stability of relationships came into picture. Okay, let's see. Yes, that's correct. So it depends, and all that it means is that it requires a closer look.
Can I assign weights to your best thing and your worst thing and just see what combinations give me a total which is
Exactly. Yes. So people have thought about this and they have exactly done this analysis. Okay, but since this came up, I'm going to, I mean, you see, because of this, I'll tell you about the history of this problem. I mean, people have thought about this long ago, really. But, there is a very nice paper called Linear Algebra Brings Marital Bliss. And, when you have such problems, they are very... So the thing is that they actually do set up weights and then they set up what is called a linear programming problem. And you can actually write down, it's an active area of mathematics. So it's, you can check it out, Yeah. This area has lots of catchy titles, because of, because of the scenario. But okay, this is the question that we want. But okay, right now we took a very special case where we have only 3 boys, 3 girls. It's very easy to just make all possible combinations and see which ones work, which ones don't. Okay. But now in community, we have lakhs and crores of people. Okay. Can we do it by a computer? Yes, maybe. If we can't do it in person, of course. We can do it by a computer, but can we do it? I mean, will the computer be able to solve it efficiently, or it will just keep running the program for ages and ages? Then the point is lost, right? So you see, the problem is really complex in real life. Okay, so before we start, let's just look at the following case. Is there a match? Okay, so now it's just 3 and 3. Yes, so we want to see if a match is possible. Then let's see if there is a stable match. Okay, here it's very easy to see with fewer numbers. Okay, but it can happen that the number of girls and boys may be different in a community. And so the whole dynamic changes, right? I'm just looking at a very simple question. So this was formulated by an English mathematician called Philip Hall. Okay, and this is known as the marriage problem. When you can all Google it, there's a Wikipedia page on it and lots of references and so on. Okay, and the premise is as follows. Suppose that a matchmaking agency has applications from n girls and n boys. Okay, let's just take this simple case. And each girl has a list of boys she would like to marry. And as boys are, no boy turns down a girl's proposal. Okay, so let's just take this situation. Okay, and in such a situation, is it possible to make a complete match? Okay, this is the basic question. So the answer is not always. Okay, why? What could be a possible problem? There may exist a girl who does not like any of the n boys. Okay, so then a match is not possible because you can't pair that girl with anyone. Let's avoid this situation. Let's say that no girl has an empty list. Okay, now is a match possible?
Not really. There may be boys with no girls list.
So we have to be a little careful. No girl has, okay, so let's think about this. Exactly, this is the worry. Okay, and so there is something called the marriage condition. Okay, so this condition.
You hide that. You are screen sharing.
I can't.
You can go to hide floating meeting controls.
Where?
Just
Oopsie.
drag it to the. Just get it
Drag
out.
it to the bottom.
Yeah, more and hide floating meeting controls.
Ah,
Yeah.
thanks. Sorry. Yeah. So, so exactly what you said is what is called the marriage condition. So as you can see, I'm already behaving like a pure mathematician and abstractifying things, right? Giving letters, assigning letters to something, doing something, and so on. Okay, so the question is, let's pick, okay, now we have seen that no girl has an empty list. So if you pick up a girl, if there is no boy to pair with, of course, it's kaput. Process fails. Okay? Suppose we take 2 girls and we look at all the boys that they are interested in. Okay? And let's see if the first girl has given a list with just one boy, and the second girl has given a list with just the same boy. Okay? 2 girls, both of them like just one boy. Then a match is not possible because you are going to assign that boy to someone and then the other girl is going to be left wanting. Okay? She doesn't have a match. This gives us one condition that suppose if you pick 2 girls, okay, then if you look at all the boys that they are interested in, that number should be at least 2. Okay? Similarly for 3. Similarly for 4. Similarly for, so if the total number is n, and if you pick randomly r girls out of them, you look at all the boys that they are interested in, that number should be in the collective list. That list should have at least r people. Okay? So this condition is definitely necessary. Okay? Clear? Condition clear है सबको? ये तो जरूरी है. Now, I think I clicked on this, right? So, okay. So, a theorem of Philip Hall. Theorem means something whose proof is established. from assumptions from 1935, 90 years ago, says that a complete match exists if and only if the marriage condition is satisfied. And what's the marriage condition? This. So if you are like a very picky mathematician like me who likes to write everything in symbols and so on, it will look something like this. No need to worry about it. Given any subset of the set of girls, the set of boys which, that are liked by at least one girl from that set should have larger cardinality larger than at least R. Forget about all this jargon. It just means that if this condition is satisfied, this seems to be a necessary condition, but it's also sufficient. Okay, yes. If you, more than is possible, at least R. Yeah, but this is about both have the same number. Total number of girls and boys is the same. Yeah, it's the yes.
A complete match just means that I can
Pair.
draw lines from this set to this set. It's not
Correct.
a stable.
No, stability we have not. We are.
Still be that
Huh.
it's
I
not
like
somebody and somebody likes me.
Yeah,
more than
that.
the ones we are
Yeah,
paired with.
yeah, exactly. That I'm coming to later. First, I'm coming to if a match is possible, then I'm coming to the next question whether a stable match is possible. Breaking it down into 2 steps. Okay. So this is a theorem by Philip Hall from 1935. Those days, even in the Western world, relationships were not so common. So everything was specified in terms of marriage. Okay. So what about stable matchings? This is exactly the question that should come to our mind. Okay. Hall's marriage theorem only addresses the question of existence, whether there is a match. Okay. It says nothing about stability. Why? Because there are no preferences taken into account. In our hypothesis, there was nothing said about preferences. It was just about numbers, very, very basic thing, whether a match is possible. Okay. Now, let us come to the point. Okay. So now everybody has given their preferences. Okay. And the question is, do stable matchings exist? So stable means what? There should be no, what I would like to call rogue pairs, like Bill and Alice in the previous example. Okay? Clear? Stability ka matlab, there should be harmony in the society.
Does that mean that there are no pairs where both people have a preference which is different than the one that they are paired with?
Exactly. So everybody is paired. Does there exist a boy and a girl who are not paired to each other, who like each other more than their spouses, their matched spouses? Okay? This should not happen. Okay? Now, again, people started thinking about this long ago. And there is a theorem, again, due to Gale and Shapley, 1962, which says that there always exists a stable set of marriages. No, it should be both. It should be, there should be preferences both ways. Yes, but I said this because in the setting of Hall's marriage theorem, we had assumed that boys were not going to reject the proposal. Boys will take anything. That's what we, so that means each boy had all girls as their preferred choices. Okay, so but anyway, we will change that. Correct. That was the thing for. Yes, but I'm going to make it more complicated. Yes, so like both the girls and the boys will have preferences. That's the real world situation. Okay, that's what I'm going to. That's what we are going to see right now. Okay, so they give what is called an algorithm. Algorithm, that means something that, so it's a step-by-step process which takes in certain input, gives out certain output, and the output is a stable matching. Okay? So And it's a very, very common sense procedure. Okay, what's the common sense procedure? Suppose that you have a community and of boys and girls. Let's not worry about numbers, whether they are the same or not. Okay, and how would the process go? Okay, boys would have preferences, girls would have preferences, and yeah, so every boy, step one of the algorithm, every boy proposes to his favorite girl, number one on the list. Okay, now each girl, now some girls receive only one proposal, some receive multiple. That's reality, right? So now who receives more than one? So look at a girl who has received more than one proposal. Okay, there are multiple. Now in that she has preferences. Okay, so now she looks at the top one. So उसने तो propose किया ही है, तो बाकी सबको reject कर दो. Okay, so rejects everyone else. Okay,
There is no guarantee that
that is number one on her list.
on her list that may not,
Exactly.
may not be there.
So she doesn't accept him yet. Okay, and keeps him on a string to see if someone better may come along.
The department reason.
It's exactly the same. That's why I'm doing it. Yes, exactly. Okay. Okay. Clear? All common sense, right? Okay. Now that's first stage. So, yeah. She knows the full list and she has her preferences. But she doesn't know if somebody else has proposed to someone else, or she doesn't know the boy's preferences. Exactly. She knows. Yes, she does know. Okay. And yes, yes, yes. But that is real life if you look at college admissions and train reservations. So it's not real life for relationships. Yes. I'm just giving a model to this situation. Yes. Okay. So now what has happened? All the boys have proposed. Some have received rejections. Okay. But some have not been accepted yet. They're waiting. Okay. This is the situation. So stage 2 is the rejected boys, they don't lose heart. They propose to their second choice. Okay. Now, again, some girls may not have received any proposals in the first round. Now they have received. Or maybe everybody received, they rejected some, they kept one guy on the string. Now they have received more. Now they have more to choose from. So they do the same thing. But again, she doesn't accept him yet. Okay. If it's her top priority, then she will. Otherwise, she will wait. Okay. So stage 3, the process continues. Okay. Some more people get rejected. And see, if you see, the number of rejected people go on diminishing. Okay. And since there are only what we call finitely many, only a certain given number of people, this will stop at some point. Okay. Girls will stop receiving proposals. Boys will have proposed to everybody, and then nothing will happen. So then they will accept. Okay. Now the question is, this process eventually stops, but then the question is, so this is the algorithm summarized. Any questions about the process and the algorithm? We don't yet. We don't yet. And that's where somebody has to prove something, if the match is stable or not. Okay. So this is the process that is given. It's a very common sense process. Okay. And so what is the guarantee that this set of marriages is stable? Okay. That's the question that naturally came to your mind. Okay. So now suppose there is what I called a rogue pair. Suppose there is a man and a woman who are not married or matched, but prefer each other to their respective partners. Okay. We want to see if this can happen, right? But then you see, men are proposing in their order of preferences. If this W woman was there, then he would have proposed to her at some point before proposing to his current wife, right? And also, because of the way the algorithm is, W must have rejected him already because she had someone better, right? So this cannot happen. Okay? Again, complete common sense argument, right? Logical argument. This should not have happened. If everybody is honest, that also doesn't happen in reality, by the way. But we are looking at an honest world. We are just assuming that all of us are computers who follow rules and we do things. Okay? Okay, so this algorithm will always give a set of stable marriages or stable matchings. Okay? Okay, anyway, this method of argument is called proof by contradiction. You want to show that something doesn't happen, you assume that something happens, and then you derive an impossibility. Okay, that's what we did. Okay, let's go back to the matchmaker's dilemma. Okay, this is something that we understand, right? We looked at this and we looked at the matchings that were made by the matchmaker, but we should be able to say something about him. So, okay, in this case, there are exactly 6 possibilities. Okay, 6 possible matchings. How? You take first boy. For that, you have a choice of 3. So you choose 1 out of 3. Then the next boy, there are 2 remaining. So there is choice 1 out of 2. And so the total number of choices is 3 times 2, which is 6. And after the 2 are matched, there's 1 pair them off. Okay, so there are in all 6 possibilities. How many of these are stable and how many of these are not, given this table of preferences? Okay, so now, okay, whether it is this table or not is not that important. But you can make your own table at home, play with this, play with the possibilities and see what you get. But if you take this collection of preferences, then you can check that exactly 3 are stable arrangements. Okay, so give each man his first choice, give each woman her first choice, or give everybody their second base choice. Okay, if you do this, then these matchings will be stable. This you can check, and the other 3 are unstable. But that's only true for this table. You see, I mean, like, we have not looked at a situation. I wanted to keep things simple, so I did not look at a situation where there was just one girl who was everybody's first choice, which is what happens in reality, by the way. Okay, I'll show you a live example in the rest of the slides. Okay, so where such a thing can happen. Okay, so yeah, so there are 3 stable arrangements and the other ones are unstable. So now that there are 3 stable arrangements, the question is, which one is optimal or fair or good or bad? Now, whenever we use these words, optimal, good, fair, bad, then we have an aim that comes into picture, some good practice, something that should happen. Okay, now we want to go towards that. So then, out of these 3, which one is better? Okay, is the question. Also, there is another question. You have seen this common sense procedure called Gale-Shapley algorithm. Okay, if you apply that here, what will happen? Which one would you get? Okay, so I'll give you the answer, but you make this table by yourself and you can go through the Gale-Shapley algorithm and see what you get. Okay, this is an exercise that you can do at home. You can get this one too because it's going to be on YouTube anyway, right? So now, what is optimality? Okay, so this is called a deferred acceptance procedure. And although this algorithm is very, the algorithm is very mechanical thing to do. Once you give the set of rules, you follow it. It's a biased algorithm. In what sense? Okay. So there are two shocking facts. Shocking fact number one. The Gale-Shapley algorithm pairs every man with his optimal mate. What does that mean? You know, in the previous slide, there were 3 stable arrangements. The Gale-Shapley algorithm will give you the first one. Okay. Now, this is something you have to go through again, this is something that has to be proved. You have to go through the proof. This is usually what is done in a good undergraduate or graduate course in mathematics or computer science. Okay. So, shocking fact number 2. Among the possible mates for a stable matching, the Gale-Shapley algorithm pairs every woman with her worst possible choice. Now, this is a bit of a surprise, right? This is something that you don't expect. Okay, but this can be mathematically proved, and this is exactly what the paper of Gale and Shapley proves. Okay, so the thing that we should take from this is that proposers fare much better than the acceptors. You know, it's not a good idea to sit on a proposal. Okay, that's the relationship advice if you want one. And also, you know, it pays to be aggressive, you know, as long as you don't find a few rejections. You are going to get the best. Don't worry. That's just a joke, okay? Okay. As I promised, I'm going to show you one in action. Okay? But now instead of 3, I'm going to take 4 girls and 4 boys. I can take more, but yes, question? No, sorry. Okay. So now the circled ones are proposers. So these are the boys. The square ones are acceptors. These are the girls. And here are the preferences of acceptors. And here are the preferences of proposers. Okay, so take some time. Okay, we are not in a hurry. So as you can see, this girl number 2 is liked by 2 boys. She's on the first preference for boy number 1 and boy number 4. Okay, and the others have other preferences. Okay, so the first step in the Gale-Shapley algorithm is that everybody proposes to their first choice. Okay, so this is the proposal pool. Girl number 1 has a proposal from boy number 3. Girl number 2 has a proposal from boy number 1 and 4. Girl number 3 did not get any proposals, and girl number 4 has a proposal from 2. Okay, so who has a choice? Girl number 2. She has a choice between 1 and 4. Okay, so we go to girl number 2. She prefers 4 to 1. Okay, so she's going to reject 1 and she's going to keep number 4 on hanging. Okay, questions? Okay, let's see what happens in next round. Okay, so now this dotted arrows are there. So they are sitting on those proposals. 1 is rejected. 4 is kept hanging. Okay, these are their current, this is their current status. And now so this is the round 1. This is the status after, I mean, as I said, 1 gets rejected, others are kept hanging. Now, the only unattached is number 1, who got rejected in the previous thing. 1 got rejected. Okay, so this boy number 1 goes to his second choice. Okay, that is girl number 1, and he proposes. Okay, now girl number 1, okay, had a proposal. So here, girl number 1 already had a proposal from 3, but she received a new proposal from 1. Okay, in her table, girl number 1, she prefers 1 to 3. Okay, so now she is going to reject boy number 3 and keep number 1 for hanging. Okay, so now her current status. So 3 is rejected. She has kept number 1 hanging, but she will accept that person because that's her top choice. Okay. So now again, 1, 4, and 2 were attached. Number 3 got rejected. So number 3 got rejected by 1, goes to his next choice. Okay, that is number 3. And then, yeah, so girl number 3 did not receive any proposal in the first round, right? First 2 rounds. So now she got a proposal from 3. So she has taken it. Okay. Now each girl has just 1 proposal, and there doesn't seem to be anything better to do for the boys. So they are not going to propose to other girls. Okay. So this is the finish. Okay. So how the algorithm works, is it clear? I just took this smallest example where accepting, rejecting, having somebody without proposals, all the cases are covered. Okay. Now, I have to point out some features of this algorithm. Okay. It's a symmetric procedures. What does that mean? So if the girls were proposers and the boys were acceptors, then the girls would have gotten their optimal list choices. Okay. And there could be these 2 solutions need not be the same. Okay. If you switch the roles, the solutions need not be the same, but they will be the same only if there is a unique solution to the whole thing, which may or may not be. Now calculating, yes, please.
There'd be a scenario where I would get a different answer.
Yes, of course, but then the preference table would change, right? You are going from bottom to up, that means you're reversing all the preferences. It's just another way of saying this.
Randomly given somebody 1, 2, 3, 4. There is no reason for giving somebody 1, 2, 3, 4. So he's already being pushed up in the hierarchy. So he may get, so if you are say
No, then assigning number 1, 2, or 3, 4 does not make any difference. See, their choices were free. See, like this table, it is free to each.
Yeah, see, 2 boys have exactly the same thing. And the person who comes first, probably he will get the choice, whereas the other person who comes later in the algorithm.
So the point is that there will be 2 boys who might, suppose they have the exact same set of preferences. But then the girl who gets the choices will have a difference between those 2 boys, and she will get the better one. And then she will, yeah, it depends upon. So the point is that this table is up to the free will of these 1, 2, 3, 4. Similarly, this table is according to the free will of this. Okay. To keep it simple, I took the situation in which there is, given 2, you have to choose 1. Okay. In real life, you will get situations where you prefer 2, equally. Okay. Yeah, please. So not in this, it is difficult because in this I have to list all the stable matchings, and then I have to say which one is. But in the place where yeah, so as I'll just go back to this thing. In this, if you run the Gale-Shapley algorithm, you will get the first one, and which is clearly the most optimal matching. Yeah, yeah. So in fact, yeah. So there's a mathematical proof in the paper of Gale and Shapley where you can actually see this. In fact, there is a more general version. I'll come to that. So yeah. So let me go ahead. Yeah. So what I want to say is that the condition that there be the same number of boys and girls is not essential. Okay. Now, again, the procedure of college admissions or train reservations is that your college is the girl. And then there are multiple boys. It has a certain number of seats. And a multiple, lots of boys are going to apply. And you don't have the topmost preference, but let's say first 100 preferences, first 200 preferences. Okay, you can write down an algorithm for it, the same algorithm, and it works. That's exactly what Gale and Shapley prove. Okay, it's the same for train reservations. Each train is a girl. It has a certain number of seats, and it takes those many applications. Okay, the point of the Gale-Shapley algorithm is that it benefits the proposers. Okay, and it's optimal because that's what we want in real life. We want the applicants, the students to benefit. And we want, again, the applicants who look for tickets to benefit, not the trains, not the colleges. And what's funny is that this algorithm, I mean, mathematically ensures that it gives the best choice to the proposers or the applicants. Okay? That's why this is fantastic. Okay? Now, of course, this received a lot of recognition. Shapley won the Nobel Prize for economics in 2012 because of this. It was jointly with Alvin Roth, who actually, before the Gale-Shapley algorithm came into existence, before that wrote down a bunch of real life applications. I mean, not just to like real life situations like this, but also to market design and so on and so forth. Okay. Gale would also have got it, but he was ineligible as he passed away in 2008. Okay. And this is the version of their paper, which is written for common people in the American Mathematical Monthly, January 1962 issue, in which they, okay, I mean, now you cannot read it, but if you Google this, you will find it. It's there on their Wikipedia pages. The article can easily be found. And so again, they look at this general situation where a college is considering a set of n applicants, of which it can admit a quota of only q, and so on and so forth. So they do the whole thing. This paper gives you all the logical arguments. This is in very well readable if you can keep at it, and yeah. I mean, if you can follow the logic carefully, it's very easily readable. And so the deeper aspects are, of course, in their research papers, which actually talk about feasibility of the algorithms that they write, whether they are doable by the computers. You know, computer scientists are always worried about how much time it takes to run an algorithm, and they give exact estimates for it. And I mean, there's a lot of work that goes on. You know, I mean, they got the Nobel Prize for economics for this. I mean, this deeper work. I'm only explaining to you the tip of the iceberg. I'm only showing the tip of the iceberg to you. Okay. There are other interpretations in other areas, like yeah, I mean, combinatorics, graph theory, computer science. There are other applications. Okay, so yeah, I mean, this is for you to explore. But now there is one unfinished business. Can you tell me which one for this talk? We're almost done, right? What's common? Now that you have listened to this talk, can you tell me, can you guess? I think we have after the chai to discuss the details, but what could be the answer?
Could be possible. What are the optimal solutions that are there? It's not connecting with the cards.
एक क्लिक में आंसर है. No. So the common principle, mathematical principle to all this, you have seen in the lecture, and that is Hall's marriage theorem. All of these are trivial applications of Hall's marriage theorem. There are no preferences involved here. Okay, I mean, whether the match exists is about Hall's marriage theorem, right? I mean, if there are too many trains, but not enough people who want to go by those trains, there will be no booking, those kind of a thing. But similarly for the colleges. But all of them are very, very simple consequences of Hall's marriage theorem. Maybe I think a chai would give people some opportunity to think about this, and and it seems to be a very good place to stop. But you know, as you know, this is just the beginning. Thank you for your attention.
Okay, I think
We can
we
take some.
quickly take questions from here.
Sure, sure.
And then we can come back after chai for questions over here. There's only actually one so far. How would a version of the stable marriage problem with 3 or more categories be interpreted?
3 or more categories, meaning so it's right now it's just a binary thing with proposers and acceptors.
Right.
Now, if you want a third player, it's a different issue. So, I mean, one way you want to do this is, I mean, let's say after 10th standard, you have not chosen whether you want to do science or commerce or arts. And then you can put that into picture as well. But what you would first do is that you would treat all the colleges as acceptors, regardless of the discipline, and do get a set of matchings or stable matchings, then put extra constraints to do it within that. But it's a more complex issue. I think also algorithmically, it's a more complex issue. The proofs, etc., are only for the cases where there is a proposer and there is an acceptor. It's not completely fixed as far as I know. I'm not a computer scientist by profession, by the way, but yeah.
Okay. Any other questions from the online audience? Now is your time to type it in. These are just comments. Thank you. Nice, etc. Okay. I don't see any more questions. So I think we will then proceed for chai and we can stop the live streaming. And thanks
Thank you.
again for watching, all those who are watching online. If you have further questions, please put them in. We can convey the questions to Anand later.
Yeah.
Okay. On that note, let's stop the live stream and let's have chai and come back. I'm sure you have enough questions for him.
Yeah. Thanks for your attention.
She was in Brand Corporation.
Yes.